But material should be pre-cleaned to remove oil and grease which may mask the surface. After pickling, the component must be thoroughly rinsed with clean low chloride water. Otherwise, smutting may occur, which is due to the presence of all of these metallic elements drying out onto the surface. But if the pickling is done appropriately, as in this case here, pickling of the weld seam on the top of the tank, we can see before and after. We have a nice clean stainless steel surface. In addition to pickling, heat tint and surface contaminants can be removed by electropolishing and electrocleaning. Electropolishing is typically achieved by immersion in an electrolyte, where an electric current selectively removes material with lower corrosion resistance and thus ensures complete removal of both dark oxide and the underlying chromium depleted layer. And it preferentially removes the peaks of surface roughness, resulting in a surface that is brighter and slightly smoother, typically a few tenths of a micrometer, and it rounds sharp corners. Electrocleaning is a kind of a variation of electropolishing. It's performed using portable machines that effectively removes heat tint, but the chromium depleted layer may not be fully removed on thick weldments. It is dependent on the thickness of the heat tint and the application time. So with regards to portable electrocleaning, this sort of apparatus is now widely available. It is effective for cleaning up weld and can replace pickling. It can be quite slow because it's all performed manually, and the electrolyte can be messy. The acid solution gets hot and will split, so personal protective equipment is required. So just a few comments about electrocleaning versus pickling. Pickling paste and electrochemical cleaning can restore the corrosion resistance of weldments after welding. Electrochemical cleaning uses mild acids, say possibly a phosphoric acid based, instead of the hydrofluoric nitric acid solutions in pickling paste. Electrocleaning is less effective on heavy black heat tint. Prior treatment by mechanical means such as abrasive blasting or grinding may be helpful. Both methods are typically manually applied, and thus they may miss portions of the weld. Wand electrocleaning is very operator dependent, both in style and in time of application. But electrocleaning is not dependent on temperature. With pickling time increases with lower temperatures, because as we know, chemical activity doubles with every 10-degree increase in degree centigrade increase in temperature. So the time for pickling would take much longer if you were doing the pickling at 10 degrees C versus say at 20 degrees C, or even say at 30 degrees C. So diving a bit deeper into passivation, we know passivation is the formation of a protective oxide film on the surface of stainless steel, or removal of surface contaminants that impair the passive film. So we can kind of divide passivation into kind of like two types. Air passivation, that is the spontaneous formation of the protective chromium oxide film by oxygen present in air or water, provided the surface is free of contamination. And this is what happens at a stainless steel mill after pickling. If they've annealed a piece of stainless steel plate, they immerse it in a bath of pickling solution. And leave it there for a designated amount of time. They remove it from the bath, rinse it with clean potable water, and the surface then spontaneously forms by reaction with the oxygen present in the air. But then we can talk about chemical passivation, which is the application of acid solutions such as a nitric or citric acid, which are not corrosive to the stainless steel, or it could even be other highly oxidizing solutions such as hydrogen peroxide. And all of these are effective in removing surface iron contamination. And in essence, for simplicity, we could also call this a decontamination process. So we have to remember chemical passivation is not aggressive enough to remove heat tint nor the chromium depleted layer. Grinding on adjacent carbon steel can cause carbon steel particles to land on stainless steel surfaces. These rust spots are particles of carbon steel. And in this photo, these rust spots are particles of carbon steel that are rusting, not to the underlying stainless steel. Though premature pitting corrosion may occur in these areas in an environment where chloride ion is present. This is the primary reason for passivation after fabrication, the removal of carbon steel particles that may have landed on the stainless steel. But there are other sources of iron contamination. It could be from, in addition to, say, just simple grinding on carbon steel nearby, it could be weld spatter from carbon steel welding nearby, or it could even be stainless steel weld spatter, because stainless steel weld spatter is highly oxidized, it has less corrosion resistance, it lands on the surface, and it could even rust and cause rust spots. Forming equipment can transfer carbon steel particles to stainless steel form with that equipment if the equipment has not been cleaned prior to its use on stainless steel, or if the stainless steel has not been protected by an insulator such as cardboard, craft paper, or plastic film. And in this photo, we can see corrosion of iron that has been embedded in a sheet of 304 from carbon steel forming rolls. And then another source of iron contamination, it's the same. It's just carbon steel dust. But if carbon steel particles can be transferred to stainless steel surface by walking or driving on unprotected stainless steel with boots or forklifts carrying carbon steel dust from other areas of the shop. Stainless steels can also be contaminated by contact with steel packing straps and handling equipment made from carbon steel, or by contaminating blasting media or stainless steel brushes contaminated with carbon steel particles. And here we can see contamination from stainless steel strap that was used to, say, bundle up this stainless steel, but there was no insulator, say, like from plastic or wood or paper between the carbon steel strap and the stainless steel surface. And in here we've got contamination by blasting media, or it could even been a brush that had been contaminated with carbon steel particles and was brushed onto the stainless steel. So a few slides back, passivation was defined as surface decontamination process that is not corrosive to the stainless steel, but simply removes surface contamination so that the clean stainless steel surface can spontaneously form its passive layer. Here we are going to see what degree of corrosion resistance is achieved after various passivation treatments. Those treatments being nitric acid, citric acid, hydrogen peroxide, and in this table here, Avesta finishing one is a hydrogen peroxide solution, and a dilute sulfuric acid, and simply oxygen and air. The last one in the table. This work was performed by Avesta, now known as Outokumpu, a major European stainless steel producer. The effectiveness of the various passivation treatments directly after pickling is assessed by determining of the critical pitting temperature of the stainless steel. Directly after passivation with nitric acid, the CPT value is the highest, say in comparison to the citric, finish 1, the dilute sulfuric acid, and air. Then all the samples were exposed to a dilute 0.5% sulfuric acid solution for 3 days, and the CPT was measured again. After 3 days, the nitric acid CPT remained the same, and the CPT for the other methods were now at least equal to the CPT after passivation by nitric acid. This shows that a clean stainless steel surface will spontaneously develop It's corrosion-resistant passive film simply by exposure to oxygen and air, and will continue to develop its optimum corrosion resistance in no more than 3 days and likely less. This is what happens with the stainless steel produced at a mill. After pickling, it simply develops its passive film by spontaneously reacting with the oxygen and air. Autocompo also measured the thickness of the passive film directly after passivation and after exposure to dilute sulfuric acid for 3 days. Initially, there were differences in the thicknesses. We can see that in the light bars directly after passivation. But after 3 days, the thickness of the passive film for all three treatments were similar. Autocompo also measured the chromium content of the passive film. Again, there were differences in the chromium content directly after passivation. You can see here between nitric, citric, hydrogen peroxide, sulfuric acid, and air. But after 3 days, the chromium contents of the passive film for all three treatments were very similar. So, some comments about the passive film and passivation based on the previous slides. The passive film adjusts itself after the environment and reaches an equilibrium state with optimum properties in no more than 3 days and likely less. Duration studies show that all treatments have the same effect after a maximum of 3 days when regarding corrosion resistance. Chemical passivation treatments after pickling are not essential, as a passive film forms spontaneously in the presence of oxygen. When applied to stainless steels, the main function of a chemical passivation treatment is to clean the surface by removing free iron and other surface contaminants. Passivation with nitric acid decreases the time to equilibrium, and the positive effect is obtained faster than for other treatments. Thus, if a weld repair must be immediately put into surface, a nitric acid passivation might be beneficial in providing the optimum corrosion resistance to that material when it's put back into service. On this chart, this table shows different cleaning methods that can be utilized to remove various types of surface contamination, such as oil, grease, iron, paint, annealing scale, scratches, weld, spatter, and heat tint. And this table can be found in our publication, Practical Guidelines for the Fabrication of Austenitic Stainless Steels, 16,001. That's shown here at the bottom of the table. And we can see here, say, for oil cutting organic compounds, various cleaning methods could be solvent, hot steam, high pressure, water, caustic cleaners. And this could be used to remove organic compounds before pickling or passivating and before any high temperature exposure, such as welding. For iron, temperature contamination is iron and steel. You could do passivation, as we described, using, say, nitric or, say, citric acid, or you could even do pickling or electropolishing or fine grinding. For paint, you could remove it by glass bead blasting or a solvent, annealing scale. You could use an abrasive method to remove a lot of it, follow it by pickling and or passivation. And so we can just basically say there are many different ways to achieve your post-fabrication cleanup, and this table summarizes many of those processes, and you can find that in the publication. But here we also have, this table summarizes the effectiveness or non-effectiveness of various chemical and mechanical treatments to remove various types of surface defects or contamination. For example, grease and oil can only be removed by a solvent or caustic solution. Heat tint can be removed by pickling and mechanical treatments, yet is still corrosion resistant enough to be immune to removal by a passivating solution. Again, this table can be found in our Practical Guidelines for the Fabrication of Austenitic Stainless Steels, publication 16,001. So we've covered everything from grease and oil, weld, heat tint, weld slag, various types of light surface iron contamination and embedded iron contamination, And we're looking at degreasing, pickling, electropolishing, passivation as chemical treatments, and then there are mechanical treatments, whether it be blasting, wire brushing, and grinding, polishing, and the effectiveness of the various surface treatments are identified with an E where it's effective, E in brackets where it might be effective, and N where it is not effective. And so even though we've talked about passivation and how to remove iron contamination, after pickling or passivation, typically visual inspection is sufficient to ascertain that the surface is sufficiently clean of contaminants. However, in some cases, minute amounts of iron contamination can be objectionable for some critical applications, such as pharmaceutical manufacture. More precise inspection methods might be required. ASTM A380 and ASTM A967 describe these methods for detecting iron contamination, and these three methods or the three primary methods are surface wetting, copper sulfate test, or peroxide test. And briefly discussing surface wetting. Surface wetting is fairly straightforward. You wet the stainless steel surface and wait. Any surface iron contamination will eventually rust. This is sometimes seen on fabrications when they are shipped from the fabricator to the customer. During fabrication, the surface of the equipment becomes contaminated in the fabrication shop, but since the fabrication takes place undercover, the iron contamination possibly doesn't rust. Then the equipment is transported to the customer and it rains during transport, and the iron contamination rusts by the time the equipment reaches the customer or while it's sitting in the customer's yard. So here, it's a fairly simple process. Wet the surface, allow it to dry, and repeat a number of times over a 24-hour period. And with respect to the copper sulfate test, this test is recommended for the detection of metallic iron or iron oxide on the surface of stainless steels containing 6% chrome or more. Stainless steels with less chromium may show a positive result. This test can be used after fabrication on select areas such as weld beads or where scratches are observed to determine if iron contamination is present. Or it could be used after passivation on select areas to determine if passivation has been successful in removing iron contamination. So it's a solution of the sulfuric acid and copper sulfate. And basically the procedure is you swab the surface and keep wetted for at least 6 minutes, and then copper deposit indicates the presence of iron. Then there's a peroxide test. The peroxide test will also detect metallic iron or iron oxide on the surface of stainless steels. The appearance of a blue stain within seconds of application is evidence of surface iron contamination, and several minutes may be required for detection of oxide scale. This test can be used after fabrication on select areas such as welds, bends, or where scratches are observed to determine if iron contamination is present, or it can be used after passivation on select areas to determine if passivation has been successful in removing the contamination. The solution is a mixture of nitric acid with potassium ferrocyanide, and for the application, it can be done with an atomizer. Blue stain should occur within seconds, and then you would thoroughly wash with water. Now, some things to realize with the use of pickling solutions. Pickling creates waste that requires special treatment. The wastewater that is produced is acidic and contaminated with heavy metals, mainly chromium and nickel. The wastewater can be neutralized using an alkaline agent such as slaked lime or soda in combination with a settling agent. Adjusting the pH value of the wastewater causes the heavy metals to precipitate as metal hydroxides, which precipitation is optimal at about a pH of 9.5. These heavy metals then would form a sludge that can be separated from the neutralized clear water. This sludge is considered a heavy metal waste and should be disposed of according to local regulations. If analysis shows that the treated water satisfies local regulations, it could be released. So the Nickel Institute, we have several publications about post-fabrication cleanup. Here I'm showing the Nickel Institute publication, Practical Guidelines for the Fabrication of Austenitic Stainless Steels, numbered 16,001. It was recently revised in 2020. And chapter 15 of this publication discusses post-fabrication cleanup, and it's free as a download at our website. And we have a number of other publications that also discuss post-fabrication cleanup, which discuss pickling and passivation. Technical assistance. So the Nickel Institute, we provide technical assistance with nickel-containing materials, which can be obtained through the Nickel Institute website. If you go to the homepage, you'll see the yellow box, and just follow the link. You can create a free account and ask your question. And since I'm the technical the coordinator for the inquiry service, I'll see your question, and I might be the one who answers it, or I would possibly be forwarding it to another individual who is a part of our group of consultants that answer technical questions. And here we just see a little picture of the pickling before and after. And now questions.
Let's see if there are questions coming in. Yes, good.
Yeah, there are, I think. No?
It's not a question, it's yes.
Yeah,
good knowledge.
It's a compliment.
Sharon.
Yeah.
Yes.
If I could just make a comment, some people may wonder why passivation or a nitric acid treatment is sort of the final step in the food process industry systems. And not only is it to remove contaminants, but the nitric acid and oxidizing citric acid solutions, it also kills any bacteria that are present. So you'll always see that in a food processing specification that you do a passivation. You might say, well, why do we need to do that if we do it clean? Well, it also kills any bacteria, especially after you do the setup at the factory.
So there is a question I can see. Is this pickling passivation is applicable for the 300 series steel?
Well, yes. Well, all stainless steels, if the surface has been contaminated, whether it's after annealing and you have formed annealing scale, or heat tint from welding, or if there's contamination, iron contamination on the surface because of some carbon steel fabrication that was performed adjacent to the stainless steel, you always want to restore the stainless steel to its original clean surface, and pickling will remove heat tint and annealing scale. And then when you rinse it with clean potable water, you allow the clean stainless steel surface to spontaneously form its protective passive oxide film. If the contamination is just kind of minor, just some carbon steel contamination from, say, grinding, well, then you would use, say, a nitric or a citric acid to remove that from the surface. And that's true whether it's a 300 series stainless steel, whether it's a 200 series stainless steel, whether it's duplex. and even 400 series. The only thing is to recognize that the strength of say if you're pickling, the strength of the acid you're going to use will determine the corrosion resistance of the stainless steel will determine, say, the strength of the pickling acid that you would use to do the pickling or the passivation. But it applies to all grades of stainless steel.
Yeah, so there is one more, Mr. Gair, that is on how effective and safe to blast martenset steel with aluminum oxide, grit, or fine size. So is it safe to blast martensite stainless steel with aluminum oxide, grit?
With aluminum oxide grade, well, yeah, you could use any material to blast any stainless steel. The main thing is primarily not to use a blasting media that is contaminated with any kind of carbon steel, because then you would be embedding it into the surface. And that's the thing, is like even if you know you're blasting with a clean abrasive, and it could be aluminum oxide, it could be garnet, it could be anything. Generally, you would generally want to do a passivating treatment after blasting to make sure that you're removing any potential contaminants that could have been carried, forced onto the surface from the blasting medium.
Yeah, so what you are telling is you will not be able to replace the pickling passivation, but it has to be done post the blasting, correct?
Yes.
Yeah. So there is one more. Do we need to do pickling passivation for nickel alloy?
Generally, you don't need to, because they are so corrosion resistant. If we talk about, say, like a C-type nickel alloy, well, C-type nickel, as I said, pickling, when you form a pit on a stainless steel, what happens in the pit is you're basically forming a hydrochloric acid solution. But like a C-type nickel alloy, well, it's corrosion resistant to hydrochloric acid at room temperature. So even if you're forming you have the heat sink and you've got, we'll say, a chromium depleted layer under it, the base metal will be resistant to pitting corrosion by chloride. So generally, with a nickel alloy, you don't really need to do pickling, but you probably would do it to remove heat tint, primarily for cosmetic reasons.
Yeah. So another question is how Fe contamination initiate corrosion?
Sorry, what was that again?
How Fe contamination, that is ion contamination, initiate corrosion?
Well, the primary corrosion that you see with iron contamination on the surface is as in the picture on one of the slides. The iron particle lands on the surface and it corrodes, and that will cause staining of the stainless steel. But if it's not a pitting environment, you won't. If it's not an environment where there's chloride present, it's primarily just a cosmetic concern. But if you're putting it into an environment where chlorides are present, well, that iron you could be forming ferric ions. Well, ferric ions plus chloride form ferric chloride, which is a very strong pitting solution.
Yeah, right.
So if you leave the iron contamination on the surface and you put it into an environment where it's a chloride solution, you could then get premature pitting corrosion underneath that particle. Also, the particle, if it's large enough, is also kind of like a little crevice. So you do always want to remove iron contamination.
Yeah, okay. And the next one is for inconel weld overlay, that is a corrosion resistant weld overlay, does that require pickling and passivation? Yeah, you could hear me?
Now I can.
Yeah. So the question is, in case of inconel corrosion
Okay.
resistant
Now I
weld
can hear you.
overlay. Yeah.
You were in and out. I still couldn't hear you, but
Yeah. Am I better now?
yeah, I hear you
Yes.
now.
Yeah. So the question is, in case of inconel corrosion resistant weld overlay, is it necessary to do the pickling and passivation?
Sorry, with an Inconel weld overlay.
Yeah. Is pickling required?
Well, here with the Inconel, we're talking about a nickel alloy again, and it kind of comes down to because as I said, like nickel alloys are generally very resistant to, say, hydrochloric acid, so they're very resistant to chloride, to pitting by chlorides. But generally, you would be doing it for cosmetic reasons, because if you've got because your customer is generally not going to be happy if he sees iron contamination on the surface rusting. So it's typically you would do some type of a passivation treatment.
Yeah.
But
So
a lot
another
of times
question.
this is something generally you would have to. It's best to discuss that with your customer.
Right. And there is one question on stainless steel casting. When it is machined, is pickling and passivation recommended?
On stainless steel castings.
Yeah, when it is machined. Yeah.
It's not. It's something that's not always necessary, because there's a lot of because if you're machining, and say you're machining with the say tungsten carbide, well, you're generally not going to be contaminating the surface. So there's a lots of whether it's a stainless steel casting or even a forging, like you say you forged flanges and things like that, they're machined. You wouldn't necessarily need to passivate it, but you might, just for cosmetic reasons. And a lot of times, like if we're talking about like a casting, say of a valve body or something like that, the outside is generally not exposed to your corrosive environment. It's the inside. So if we're just talking about the outside, it's maybe not as necessary, but it's probably good practice just for cosmetic reasons. But if you were, say, machining with high-speed steels,
Yeah.
you might really need to ensure you passivate.
Okay. I think we have covered almost all the.
I saw there was a question on providing purging. What, in addition to purging, what means and ways to reduce or avoid heat tint during welding? Well, the main ways is by using a flux-based process or purging.
Yes.
And in most general fabrication, even when you do that, you still get heat tint, and you generally need to do something, particularly if you need to do some kind of pickling or passivation if it's going to be in an aqueous chloride environment.
Correct.
What are the causes of pitting after pickling process near weld joints? Well, I'm not sure when they mean near weld joints. If you've done the pickling properly, you've removed the heat tint, you removed the chromium depleted layer, and if you've got pickling now in the weld area, it would primarily be because of roughness. like the surface of a weld is rougher than the original base material. And as we saw in one of the charts, a rougher surface is less resistant to pickling, or not, sorry, less resistant to pitting than a smoother surface. That's the only reason I could think of why you might be still getting pitting. And if the balance of the material is fine and it's just pitting in the weld area, it's probably just surface roughness. I see another one here. Suppose I'm using a grinder to remove heat tint, then a thin layer of passivation is damaged, and how to recover the chromium layer. Well, the formation of the passive film is spontaneous in the presence of oxygen. So when you damage it, it's immediately starting to reform. So there really isn't anything to do, as we saw in the various work by Otto Kampu with where they did passivation with nitric and citric and hydrogen peroxide, and then just in air. A clean stainless steel surface will spontaneous. Well, in the very first slides we saw that the stainless steel is spontaneously forming its passive layer, and it's a lot of it is done within the first 10 seconds in exposure to oxygen. But it could take a day or more, maybe up to 3 days, for it to develop its optimum corrosion resistance. So there's not something that you need to do to reform the passive layer. It just forms spontaneously with oxygen.
Yeah.
But you may want to do something. It may be cosmetically unappealing, and you might need to do some fine grinding or something.
Yeah, there are some similar questions.
Oh, I see.
Like,
I see one here on laser cleaning, substitute pickling, and
Yeah,
get
yeah.
the same effect. Well, you can use these laser cleaning to remove heat tint, but to me, it's kind of the equivalent to blasting. Like, there's no way to ensure that you remove the chromium depleted layer.
Yeah, right.
But you could certainly use it, but it doesn't really replace pickling, because you can't ensure that you've removed the chromium depleted layer.
So there is one interesting question: is paint markers and solvent markers allowed on stainless steel and other white metals? Paint markers.
Yes. Well, anything on the surface is a contaminant, and if it's then if you put the material into that stainless steel into an aqueous corrosion environment, because any markers will likely have chloride in them. There is no such thing as a marker that is 100% free of chloride. So if you put that stainless steel into service in an aqueous environment where chloride is present, and therefore you could have pitting, you could have premature pitting corrosion where the paint marker has been applied. So it's just one of the potential contaminants, and it shouldn't be there.
Yeah, thanks, Gair, for taking all these questions and the wonderful presentation.
My pleasure.
Yeah. So if any further question comes up, we will connect it through Jerk so that you can reply to those.
Well, yeah, and as one of the last slides, they can just go to the Nickel Institute website, click on technical assistance, create a free account, ask their question, and they'll have a response within a day or so.
Yeah, sure. Yeah. Okay, thank you so much. Thanks, Gary. Thanks, Jug. Thanks, Mr. Graham. All of you for joining
Thank
us
you,
today.
and to everyone.